Okay, guys, this is August 2023 exam. That is the question paper that we are going to look into Mechanotechnics N4. Remember, I promised that we are going to check question papers, full papers, as we are going to be revising towards our exam. So after this, we're going to work with the November 2023 exam so that you'll be able to prepare yourselves for the exams that are ahead of time. We are just a few days to our exams. So if you're someone who is into a better grade, this is the right time for you to utilize this at Maison African motives. So I'm not going to waste much time, guys. This is question number 1, which we know that is the workshop, a lot of this, so there are a lot of things that are considered there. So we are given the first part, name 5 characteristics of individual production. Remember, the individual production where we are dealing with one item. That is the idea there. So we are having, all right, the demand of the for the product is limited. One product is produced at a time. That is the individual production. That is the major part for our individual. One product at a time. So the production is labor intensive, highly skilled labor is required. It requires a fixed position layout where machines and equipment are assembled in one place. So that is the idea there. So we had this part, guys, that is just to mention or to talk about the characteristics that we see on an individual production, individual. All right, then let us check the other part of our question where we are given, in this case, that was to make a neat labeled sketch of a salt spray test for corrosion resistance. All right, so what I'm going to do with time, I'm just going to show you guys the part of our theory and our diagrams. All right, so this is the diagram that you need for a salt spray test corrosion resistance. You're supposed to label all the parts that you're given there. Every part is supposed to be given. So I think that diagram was clear enough for you to obtain the 5 marks. And we are given to name 5 factors to consider when choosing a lubricant, in this case, a lubricant. So when you're talking about a lubricant, okay, that means things that you can consider. You can talk about the price of lubricant, the operating temperature, the clearance, the rubbing speed, and also the rubbing pressure, the pressure that is being given as the rubbing pressure. You're supposed to consider that. So this is part of your theory, guys. I hope you are someone who just has to work this and make sure that you do revise properly. All right, so this diagram is just a little bit slanted, guys, as you can see, but I just hope it will make sense as we are answering this. So we are given on 2.1, fig 1 below shows 2 identical rollers. So these are identical with the diameters 25 millimeters, diameter 25 millimeters, diameter 25 millimeters this side. We talked about this type of a question a lot of times. All right, which are being used to check the accuracy of to calculate the distance x across the inside faces of the rollers if the angles have been correctly machined. There is an angle 58, there's an angle of 62. The angles are different, but the rollers are identical. It's only the angles that are different. So sometimes they can give us identical points here, whereby the angles are the same. All right? So it depends with the type of question that you are going to work with in that particular section or in that particular paper that you're given. All right. So this is what I want you to note on this part. If you check along this line that you're given, which is along the 120 there, you are going to see that this 120 here is limiting us, all right, somewhere there. If we take this straight, just to something like this, it's going to make sense. Then we do the same thing around here. All right, let's say we take this one straight. Okay. I just want you to see something here that is happening. I want to focus with the distance of 120, like I said before when we did this type of a question, that if you are to consider the distance of 120 millimeters, it consists of the x. So meaning to say we can find the x within this 120. We can take advantage of the 120. So if we take a closer look on our diagram here, there is a distance that is, let me try to increase a little bit so that we see where our 120 is starting from. Our 120 is starting here. This is where we are starting, and we are ending here. That is where our 120 is. So meaning to say, one, we are considering the condition of a radius. If you take along this line straight here, we are considering to have a radius up to the point where x is starting here, where your x is starting. We have a radius to be taken there. So we have got a radius, meaning to say our radius diameter over 2. Remember, our diameter is what? 25 millimeters. So that will be 25 over 2, which is 12.5 millimeters. All right, let's see the same thing. We have got a radius also on this side where x is ending. Remember, x is ending here. So we have got a radius again from this point to the center. There is a radius there. All right, but now the concept is that, are you seeing that there's a distance also between this one? This one is not a radius. Look where the radius is ending. If you take from the center here, let me put it this way. I want you to see this. If you take it from the center point, this is our center point, this one. From this point going up to here, this is your radius. So are you seeing that the distance that we want where our 120 is, this one, does not involve the radius? The radius, there's a piece of radius, there's a piece of another, the piece of a radius that is remaining there. We don't want that. It is not involved as part of this 120. The 120 is starting from here up like this, and it is ending there. So you see a piece there is remaining of a circle, which is a piece of a radius. It is not there. It is not involved. So the distance that we do want that covers the 120 is this distance from this point up to this point that we do not know. And from here to here, that is the radius. From then we talk about the x, it's involved. Then from here to here, which is the radius, then we talk about the same distance, but it is different because of the angles. This is 58, this is 62. So these two are different. These two distances, they are different. If these angles were equal, these two distances was going to be equal. But so since they are different, I'm going to name these points differently. I mean, this distance is this one. I'm just going to call, let's just put y, a small letter y like this. Then this one, I'm just going to put a small letter z. All right. So we need to calculate this y, this one. And we also need to calculate the z. All right. We shall talk about that. How do we calculate that? But for now, let us formulate from the 120. Like I said, that is where our x is found. So remember, we need to find x. And x is found from the 120. So from 120 millimeters, it is going to follow that the 120 millimeters is going to occupy what? It is going to take up what we have, which is in this case, this y, this one, this y, this one. All right. So in this case, let me just put as points. If I take it at the center, all right, if I take it this way, if I take it at the end point like this, if I put it this way to the end point and back like this, I'm forming a right angled triangle. If you see, it's a right angled triangle there. And this distance y, this one, is the same as this distance that we have here. So let us just call points. We can just name our points. We can say this is the origin, this is the center. So it's just going to be O. And this I'm just going to call it A. And this I'm just going to call it B. So it means y, this one is the same as the AB. Guys, this is the same from here to here and from here to here. So if I calculate AB, I'm calculating what? I'm calculating y. I do the same thing from this side. If I join from the center to this point at the end here where the line is, and here I'm formulating a, okay, someone is asking, why are we formulating a right angle triangle? Remember, this is a radius, like it's a circle, and this line here, it's a tangent. So we have got a tangent there. Remember, a radius, when it meets a tangent, they meet at 90 degrees. So it's a radius and a tangent concept there. And also, if you take a closer look, what is happening at this angle here, this angle that is taken here. All right. Let me just remove this. I hope now you understand about this line. So I'm just going to remove it. So we just finished this. I'm just going to remove this line. I hope you see where it was taken from like this. All right. I'm just going to remove this line as we know where we want. Okay. So I'm just going to remove this line so that we'll be together. I'm just going to remove this up to here so that we properly see what I'm trying to say here. Remember, this is the distance that we want here up to this set like this. I'm just going to put it this way. All right. I'm just going to up to this. This is what we want from A to B. But the reason that I'm erasing these lines is that we want to properly see the concept of the angles. Yes, we are agreeing that it is a right angle triangle, which is true that it is a right angle triangle here, a right angle triangle here. But what about the angle here inside of this triangle? What is going to be that angle? Okay, the concept of that angle is that one, this is a straight line. So we know that angles on a straight line, they're up to 180. So we are going to remove the 58 degrees from the 180 degrees. All right, that's 180 minus 58, which is going to be 122. The whole of this angle up to this point here, the whole of this angle is 122 degrees. But now from our concept of the tangent, because this is a tangent, this is a tangent. And I said, if a line is drawn from the center to the point where the tangent meets, this line, as long it is from the center, it divides these two angles into two equal parts. So if these two angles are being divided into two equal parts, what does it mean? It means I'm just going to simply divide this by 2. So this means there's a 61 degrees. This is going to be 61 degrees. So this angle will be 61 here, and this angle here will be also 61 degrees. All right, I hope we are together, guys. So we are going to see this in our simplification. So it means in this triangle, let me just put it aside. I'm just going to call it triangle OAB. In triangle OAB, it's like this. It's a right angle triangle. This is O, this is A, this is B. So the angle at O, this one, this is the one that we are saying it is the same as this, which is what? Which is 61 degrees. So if you check, we can be able to calculate AB. Why? Because we know that from this point O to B is the radius. It's the same. From the center to the end of the circle, that's a radius. So OB representing the radius, and the radius is what? Is 12,5. So we have OB, which is 12,5. So we can be able to calculate AB from there. We are able to calculate AB from there. So it is the same thing that you're going to do even on this side, all right? You can also do the same thing on this. We're going to come back and calculate our AB. I just want you to see. All right, so there are different approaches there, guys. All right, I just want to remove this, sorry. So if you check on the other hand, because these angles are different, we're supposed to just take it as AB and also this one as AB. But now these angles are different. So this one, we're just going to call it O. Then we can even call this E and this end point as F. So it means we need to calculate EF. Just like the previous case, to find this angle, it is the same as the remaining angle on the other end. So it's 180 minus this. Just like what we did on this side, 180 minus 58, then we divide by 2. So it's going to be 180 minus 62 degrees, then we divide by what? We divide by 2. That means we are having the angle that is going to affect on this other side. All right, and that was going to be 59 degrees, something like that. And this is 59 degrees. So it means inside of this triangle, there's a 59 degrees. So meaning to say, if there is a 59 degrees, the triangle is going to be like this. I want you to see this. Okay, sorry for that. Sorry for that, guys. I want you to see this because we've been talking about this, but guys, you're now supposed to know or to understand this. So you're supposed to have something like this from O to E to F. All right, let me just push it aside. Sorry for that. Let me just push it aside because it's going to affect. All right, I said it's going to be like this from point O to point E to point F. These are all your own points. You can even call whatever that you want here. So you see that from O to E, it is the same thing as the radius. From O to this point is the radius from the center to the circle. So that means we've got 12,5 just like the previous case. So this is 12,5 millimeters. We want to calculate EF. but we are saying the angle here at F, which is this angle, is the one that we calculated here. And we said is what? It's 59 degrees. So these are the two triangles. So it means we can be able to calculate what? EF. So think about those things before you formulate your equation, because you formulate an equation of something that does not exist. That's something that it does not exist. So as you can see, we are able to calculate AB, we are able to calculate EF. EF representing what? EF representing this distance of Z, this one, this Z that we are seeing here, and the EF, they are the same. Just like what I said here, the distance that we are having between Y and AB are the same. So Y and AB is the same. This Z and EF are also the same. So I'm just going to write in terms of AB and EF. We can write even Z, whatever that you want. So AB, 120 millimeters, this one, the whole of this is going to be what? From A to B, we can calculate that. We saw it, plus from B up to this point, which is what? Which is the radius. So there we have got the radius, plus from where the radius is ending, this one, X is now involved. So we're going to add X. Then from from where X is ending here to this point, E to here, it is representing what? The radius. Then from where E is ending here up to the end point, we are talking about what? EF. So we are going to add EF. The whole of this part, it gives us 120. So we have formed an equation for 120 involving X in that equation, which is the one that we are supposed to calculate. We can be able to solve for X because we can determine AB and EF from these two triangles that we are given here. So from the first triangle, how can we calculate AB? According to this angle, this is the opposite, and AB is the adjacent. So which ratio are we going to use from our SOHCAHTOA concept? Remember, from our mathematics. So that will be the ratio of a sine, TOA, all right? Tan, meaning to say we have got the tan of 61 degrees, which is equal to the opposite, which is 12,5, over the adjacent, which is the AB that we want to calculate here. So we can be able to calculate this AB. All right. So you're going to cross multiply. After that, you divide by tan 61. So it means AB is going to be 12,5 over tan 61. So like I said, you cross multiply first, then you divide. All right. So 12,5 divided by tan 61. This is going to give us AB, which is 6,929 millimeters. We have AB there. All right. So that means AB can be calculated. We have it. Right? We do the same thing on this triangle to calculate EF. So from this triangle, we are going to calculate EF. So here, let us calculate EF. So what's the concept? Just like the previous case, what are we given according to the angle here? This is the opposite. And what about EF? It is our adjacent. So we are back opposite adjacent, the tan. So that means the tan of theta in this case. All right, the tan of theta, which is our angle of 59 degrees, is equal to the opposite, which is 12,5 over the adjacent, which is EF. Just like the previous case that we had, we managed to calculate AB. Now we can calculate EF with the same concept. Just cross multiply, then divide. So you will see that EF is going to be 12,5 over the tan of 59 degrees. That's the idea there. That's it. That's it. So that means we can obtain EF from there. EF is going to be something like 7.511 to 3 decimal places if you are using 3 decimal places. I did not check the instructions there. That's another mistake that you're not supposed to do in answering. But already I've already used 3 decimal places. Okay, it's fine. I did not check that. Okay, so this is it, guys. With the AB calculated and the EF calculated, what we are going to do is to substitute them back to find AB. To find X. Since we now have this, we can be able to calculate our X. we are able to calculate our x in this case. So what does it mean? We are just substituting our information. We are just substituting our information there. So what does it mean, guys? I can make this the subject. It's either I can make x the subject, or you can just substitute. Guys, this is up to you. 120 is equal to AB. We calculated our AB. That was 6.925, right? 6.929. So 6.929 plus the radius. Remember the radius, according to our question, the radius is 12,5. So we have got 12,5 plus x, which is the one that we need, plus the radius again, which is 12,5. So this is plus 12,5 EF. We calculated EF before. We got our EF from this. Our EF was what? That was 7.511. So that is plus 7,511. So combining everything that we have on the right-hand side, what are we going to have? You add this to this, to this, to this, everything together. This was going to give us 39,44 plus x. So to find x, I can simply transpose this to the other side. I subtract them. That was going to give us 80,56 millimeters, which is equal to x. So therefore, that is the value of x there. So as you can see, this is a mathematical approach, your geometry and everything combined together. You'll be able to answer this type of a question. You'll be able to answer this type of a question. So that's it. That's you guys into mathematical approach there. All right, so we are going to check another question, but that was it there. As we can see, it was actually 8 marks. Okay, let's see the other part that we are having, second part of our precision measurement. There we are given, let us consider our diagram. All right, I've actually talked with this type of a question again. So these guys, they are just repeating. It's a repetition that is happening throughout. But it's fine to us, guys, because you'll be knowing exactly what you're supposed to do, because it's a repetition here. Fig 2 below shows a roller with 2 sets of gauge blocks of 12,75 millimeters each. The distance from the bottom of the groove to the top face is 70 millimeters. The distance from this point, which is the groove, up to the top, which is this one. And we are also given, there is a 12,75, this one, in between here. This distance is what is 12,75 millimeters. So use the given dimensions to calculate the diameter of the roller. We need the diameter of the roller, given that we have got an included angle there at the groove of what? 60 degrees. All right, and we need what? The diameter. All right, I have said this. We have talked about this question, so I'm not going to waste much time. I'm just going to quickly do this one. We are now having the knowledge on this one, guys. I said here, you work with the vertical distance, all right? From the vertical distance that we are given here, somewhere here. Let's hope, guys, I'm going to win. This vertical distance that we are seeing here, it can help us to find what the diameter. Why? All these values that we have, they are vertical values. We do not have values that are in the horizontal. If we were given values in the horizontal, we work with the horizontal. But there we are given something only in the vertical. So we are supposed to think along the lines of the vertical point. And this, we know that this is an included angle, where I talked about this, that it is bisected. As you can see, it is being joined up to the center of the circle. And from our tangents, these are 2 tangents drawn from a circle. I said they bisect this line, it bisects this angle into 2 equal parts. So the 60 that we had, this one, it is going to be bisected, divided into 2 equal parts. So it's 60 divided by 2, which is 30 degrees. So what does it mean? It means that the angle that we are having on each piece, on each side, is going to be of 30 degrees. All right, the angle on each part, this one, we're going to have at 30 degrees, and this side, we're going to have at 30 degrees. That is what it means. All right, let us just name our points along this vertical line up to its ending point, because as you can see, the distance is starting here and is ending here where the groove is starting. So meaning to say we are supposed to talk about or to think from this starting point up to the ending point. So let me just call this point A, all right, and this one B. But am I going to need this? I'm not going to need this, guys. All right, no problem. This I'm going to call it C, and this, okay, let me just put my D here. These points, you can name them the way that you want. I'm just putting the way that I did on my constructions. All right, so we are going to need this. Why am I starting at B, guys? Why am I starting at B? This is A, B, C, D. Okay, so if we check, we are going to see that from A to D, it is the radius, this one. From A to D, this is the center, so we've got the radius there. So we need the distance from D to C. This distance, it involves of the radius and this distance here in between this one that we do not know about. So to separate it is going to be difficult, because this one, where are we going to find this? This one, where are we going to find it from? Which formula, which shape do we have there? So it is best for you to take it as it is, from O up to C, the whole part as it is. We need to calculate this length, but how can we calculate it? We are stuck again. But we can't be stuck, because this is it. A tangent and a circle here. We know that if a point is drawn from the center to the circumference of the circle, and it meets a tangent, this line is not just an ordinary line. It is it's a radius, but it's not going to have ordinary properties. No, it is going to meet the tangent at 90 degrees. So it means this triangle here, let us just call, we have got D, let us just put E here. So it means triangle OCE is a right angle triangle, and you can calculate, where am I saying, oh, this is D. All right, we can even call it O, but already I've called this D. So DCE is a right angle triangle. DCE, it's a right angle triangle. So we can be able to calculate what? To calculate DC. Why? Why is it that we can be able to calculate DC? Because from D to E, remember, it's what? It's a radius. We can't use this one. Someone will be asking, why can't we just take this one? No, this one, look, it's out of the circle. Yes, it meets this line, but it is meeting this out of the circle. So the properties of a tangent does not, because a tangent must meet a circle. So there you do not have a theorem to use. You'll be stuck. You don't have a theorem to use there. So that's why we join to the circle. To the circle. So from O to the point E at the circle, this one, it's a radius. That's a radius. So we can take advantage of that. That is a radius, and we can be able to calculate what DC. So that means in this case, guys, on this question, we are done. If you can be able to understand this, we are done. Why? From the vertical distance, since we want to calculate the diameter, from the vertical distance, from the vertical distance, we are going to see that the whole combination of this AB, everything that we are seeing there, everything that we are seeing, it is the addition of these numbers, because there we have got numerical values. We'll see that if we add 12,75 to 70, we are going to obtain everything that we have in this vertical distance, which is what? From A to D, which is the radius, plus from D to C. That gives us what? The vertical distance. It can't be different. So we have written the vertical distance in terms of numerical values and also in terms of unknown values. Since we understand that the diameter is simply twice the radius, 2 times what? The radius is the diameter. So if I can be able to calculate the radius, I'm done, because I'm simply going to multiply that by 2. So this one, it's fine. So we need to think about DC. Since we do not have numerical values, it means it's difficult for us to calculate what? to calculate DC? Because we do not have numerical, we do not have anything there. If maybe we're given EC as 7, we take that to calculate, but we do not have anything. So we are stuck. So what are we going to do? We are going to calculate the DC, this one, this DC, in terms of the radius. So we are going to calculate this in terms of what? In terms of R. If we are able to calculate this in terms of radius, remember, if we can be able to calculate radius, we are able to calculate what? The diameter. So in terms of R, we are going to take the right-angled triangle. If you see, we are forming there a right-angled triangle, D. All right, why am I taking it this way, guys? I just want to take it as it is from our diagram. This one is a vertical line. So like this, we are forming a 90 degrees where it is going there. This is forming a 90 degrees there. All right, this is straight like this. So this is our DC. We have got a 90 degrees that is being formed at this point. And this is your radius, which is going to E. So how can we calculate this knowing that the angle here is what? Is 30 degrees. From our ratios, according to 30, this is our opposite. What about DC, the one that we want to calculate? It is the one that is facing 90 degrees. So it is the longest side, which is our hypotenuse. So from our soccer tour, opposite hypotenuse are found on sine. That means it is going to be the sine of 30 degrees is equal to the opposite, the radius over the hypotenuse, which is the side that we want, which is what? Which is the DC. So that is over DC. That's the idea there. So meaning to say we are able, or we can be able to calculate DC. Because remember, what we want is to find DC. So if I'm to cross multiply this and divide, it's going to be like this, DC, cross multiply this. So it will be DC. The sine of 30, you divide by the sine of 30, so it will be R over the sine of 30. Remember, we want DC. So how do I simplify from there? It's going to be 1 divided to sine 30. 1 divided to sine 30. So it means DC is equal to 1 divided to sine 30. That's a 2. But it's going to multiply what? It is going to multiply R. So DC in terms of R, like I said, this DC is going to be found in terms of R is equal to 2R. So with this DC, which we have in terms of R, we're just going to substitute here. All right. So if we add this, that will be 82.75. So 82.75 is equal to R plus DC in terms of R, which we said it is what? It is 2R. So this is 2R. So there we can calculate the radius. This is same as 1. So it's 82.75 is equal to 1 plus 2, which is 3. So that's 3R divided by 3. Divide by 3. We have the radius there. So the radius is going to be 82.75 divided by what? Divided by 2. And that is going to be 27.583 millimeters. Therefore, we can be able to determine what? The diameter from there. So therefore, the diameter is 2 times what? 2 times the radius, which is 2 times 27.583. So that's the diameter is going to be 55.166 millimeters. Just like that. Just like that. So this is the concept on how you answer these questions, guys. You just have to be careful on your simplification. You just have to be careful how you attempt your questions. All right, no problem. Let us check this one. Question number 3, where we are given a reduction gearbox, a compound gear system. All right, so there we are given, that's question 3, a compound gear system of a reduction gearbox is shown in figure 3. The system consists of the input gear A. All right, let us just check our diagram. What is it that they are talking about? So this is it. We've got the input gear A, which is our driver in this case, and this is it. All right, let's just see what we have there. I think everything is fine. We have with 68 teeth rotating at this. All right, that is at A. So at A, 68 rotating at what? 850. And an intermediate shaft on which 2 gears B, C with these teeth respectively are mounted. All right, so there we have got an intermediate shaft where B and C are being mounted and to the gear D and so forth, which is here B and C on the intermediate shaft there. All right, which is fine. No problem. So let us see what is happening here. We are given about A. This is the input. So remember, A is going to drive B. So A, this one is your driver. It is driving what? Driving B. So B is going to be the driven. So B and C mounted on the same axis, meaning to say that the speed at B and the speed at C, they are going to be the same. And that means that it is going to affect the movement of D. It is going to affect the movement of D. It is going to affect the movement of D. So the movement of D, it's a combination of B and C combined in order for us to have the movement at D. But C now is now representing what? C is now moving. It is now our driver, which is going to drive D. So D will be the driven at the end. All right, so there we're not going to waste much time on this question. They gave us that the system, it consists of the input gear A with 28 teeth. Gear A, it has got 28 teeth. So on gear A, we're given the number of teeth here, TA, which is 28. No problem. All right, so guys, let me write this. We are going to need this information aside. And 8,500, which is the speed. If you take back on our diagram there, it was 850, not 8,500 revs per minute. All right, then B, we were told that about the B, that these 2 points, B and C, with 136 and 70 teeth. So there we are given the number of teeth, which is affecting at B. TB is 136, and at C, TC is given as 70, respectively. And at D, we are given at the end, if you checked it properly, it was 100 teeth. That is what we had in that case. All right, so guys, let us quickly take this information. And also we are given that if this gear system has a module of 6 millimeters, calculate the following. So we have got a module of 6 millimeters. So there we are being asked to calculate the following. The first question was the rotational speed B, C, and D, 7 marks for that. So how can we find the rotational speed that is affecting at B, at C, and at D? Remember, from the ratio that we have from the product of the number, the speed, and the number of teeth, we can be able to calculate this speed at what? At B, C, and so forth. So let us start with the B. So remember, the product of NA times TA, which is the driver, is equal to the product of NB, the driven one, which is the driven is going to be NB TB. As we want NB, so we can divide by what? By T, B both sides. So if we divide by TB, it means our NB is going to be this formula, NA times TA over TB. All right, so that will be over TB. That means our NB is going to be NA. We just substitute, guys. We have got everything, 8,500. So this one is the simplest question, times 28 over TB, which is 136. So this one is the simplest question, guys. I do not want to lie. So that will be 425 revs per minute. All right, so that's our NA. Then remember what I said, or NB, I mean. Then our NC is the same as NB because they are mounted on the same shaft, they're on the same axis. So NC is equal to 425 revolutions per minute. We talked about this. All right. Then about D now. About D, this is what I was saying, that we are going to see that. Let us just put it this side. About D, guys, be careful about D, because D, it's a comparison, it's a combination. That's why I was saying it is from here. From here, we entered here. So it is going to be affected by everything. So you consider everything. So how do we consider this? To find it, ND, this is the formula. To find ND, you're going to consider this. It is going to be NA on the driver. Remember the driver, the speed of the driver. Then about the teeth, remember it was supposed to be NA and so forth. So this one, you are going to have the product there of driving gears. Product of driving gears. This must be equal to what? Where are we? D. So the input to the output, the driven at D. So you're going to have ND to the product. ND is the driven. So it takes the product of the driven. Take note about this one. Driven gears. So what does it mean? It means that NA times these ones, we are talking about the teeth, the number of teeth. So on them, driving, what is driving? The driver, it's A, so you're going to talk about TA. Which else is the driver? C, it's also the driver, so you talk about TC. It must be equal to ND times the products of the driven. What is driven? B is the driven. So it's going to be TB. What else is driven? The D itself, which is TD. Remember what we want. It is to find ND. So we can be able to find the speed there. How? Divide by this. Divide by TB, by TD. Divide also by TB, by TD. So this will cancel. You are remaining with the speed at D. So that's NA. Remember NA, it was 850. Multiplied to TA. Remember TA, it's 28. Times TC. TC, it's 70. Everything over what? TB, remember TB is 136 times TD, remember TD is 100. This gives us the speed at D. So that means our ND was going to be in revolutions per minute. The speed that was going to affect there was going to be 297.5 revolutions per minute. So take note about that. All right, take note about that. No problem. Let us check the other question. 3.2, the addendum and dedendum of the gear teeth. The addendum and dedendum. So these ones, we just need the formulas, guys. So from the textbook that I'm using, guys, it states that this addendum that we are talking about is simply equivalent to the module. The addendum is equivalent to M, the module. And our module is what? 6 millimeters. All right. Then if we talk about the dedendum, this one, it is the product, this one, dedendum, it is the product of 1,157 times the module. So you multiply to the module. This is the formula. So it's going to be 1,57 times the module, which is 6 millimeters. So that will be what? That will be 6.942 millimeters. Maybe they might use another value because this is just an approximated value. They might use maybe 1,16 or maybe 1,2. Just check the textbook that you're using so that we'll be together. We talk about that. All right. Then this one, they are saying the center distance X. So let us go back to the diagram. I want you to see how you take the center distance. The center distance, you consider also where it is being affected, X. All right, let us just remove some of these things, guys, some of these things here. So like I said, the center distance, you also consider where it is being taken. It is X. X is this one. Look where X is. X is affected at where? At gear A and at gear B. So you must work with the speed, with the teeth of A and the teeth of B. Remember, the formula for center distance is like this. Center distance is like this. Let us just remove this, guys. I just need to remove this. Very sorry for that. Very sorry. So remember that your formula for the center distance, this is 3.3. So we need the center distance, the one that is affecting for X. So remember, it is the module over 2. Then it is the product of the number of teeth. So since we are focusing with A and B, it's going to be TA plus TB. You focus with where X is taken. X, Y is from what? TC and TD. If you do it like that, you're done. Remember your module, guys, it was 6 millimeters. So 6/2 times the TA. Remember TA, it was 28 plus TB, it was 136. So this is going to give us the center distance for X, which is 612 millimeters. So that's what you simply needed. Just like that, you are done. So it was the same thing about the next question where they need the center distance Y. So the center distance Y, like I said, you just need to check which gears are affecting that center distance. The center distance for Y is affected by which two gears? The gear here, Y is from here. It is the center distance of gear C and gear D. All right, so that means in this case, the center distance affecting Y in this case is going to be the module over 2 times the teeth, the number of teeth that we consider. Y, we said gear C and what? Gear D. So it's going to be TC plus TD like this. So that is the formula. Just like the previous case, you just need to substitute your values in this case. All right, so let us substitute our values. So that is the center distance module over 2 times TC. So TC is 70 there. So that is 70 plus TD, which is what? 100. So that was going to give us the center distance of 510 millimeters. This is the center distance Y. So this is it, 15 marks. Just look, guys, 15 marks for just this information. So you see that under exam condition, you will be gone to take 15 marks. You need another 15 and another 15. You are 45 marks ahead. You are now 45 marks. You have already crossed half. So guys, that is the idea. That is the idea. You need the formulas. You need the formulas. Just take from number 1 up to number 3. We have already covered 45 marks. We have already covered 45 marks. So you see, Mechanotechnics, guys, you can totalize this. You can totalize this paper. I'm telling you the reality on Mechanotechnics. You can have a distinction. Just know your formulas only and follow steps. All right. So question number 4. This was belt drives. Okay. These are belt drives. So let us see what we are given here. We are given that a large pulley with a diameter of 1,300 millimeters rotates at the speed of 230 revolutions per minute. Determine the belt velocity if the belt is 10 millimeters thick. There is the thickness there. So this was a direct question also. This was just a direct question, guys. If you consider this, our diameter there is, if you divide by 1,000, that will be 1,3 meters. The speed in revolutions per minute is 230 revolutions per minute. The velocity is the one that we are supposed to determine given the thickness of the belt of 10 millimeters. If you divide by 1,000, that will be 0.01. All right, in meters. So we've got the thickness. Remember, guys, the belt velocity, if we are given the thickness, this is supposed to be V is equal to pi. We've got this formula from our formula sheet, D plus T times N, like this. But this N is supposed to be a speed in revolutions per second, revs per second. So how do I consider this formula? Okay, let us just substitute 1,3 plus our thickness, 0.01. times the N, you divide this by what? By 60, so that it is what? Revs per second, because you're supposed to have your answer in revolutions per second. This gives us the velocity in what? In meters per second. So that was a direct question, like I said, 15.776 in meters per second. We were done. All right, so that was just direct, just needed information, 5 marks for that. Then we are given the following particulars apply to an orifice provided in the side of a tank. All right, so this is taken from an orifice. So remember the idea of our orifice, guys. So we have got the part that has got the vena contractor on the orifice, which is the throat. And we've got the part of what? of the orifice, which is the one where we are going to obtain the theoretical values. All right. If you're talking about theoretical area, theoretical this, it is from what? From the orifice. So we've got the diameter of the orifice. So that is the diameter of the orifice. Let me just write it down here. So this is the diameter of the orifice, which is in meters. If you divide by 1,000, that was going to be 0.03 in meters. The delivery, it is given in cubic meters per minute. As we know that the delivery must be cubic meters per second. That is what we know about the delivery. So we are supposed to divide by 60. Remember, 1 minute is 60 seconds. So if we divide by 60, we're going to obtain 0.0125, something like that. So the delivery is 0.0125 cubic meters per second as a time. As cubic meters per second, the time per second. The units, they are very, that's why I'm even writing this in meters. Why? Because the diameters, all these, they are supposed to be in meters. Then the diameter of the vena contractor is the diameter that is affecting the throat. So it's the actual diameter in this case of the vena contractor at the throat, which is 0.025 if we divide by 1,000 in meters. Then the pressure head, which is the height that we're given in between. Remember, we are talking about the distance, that is the height of water, is called the pressure head. So the first question was to calculate the following. We are dealing with the coefficients there, the coefficient of delivery. So we just need the formulas there, guys. These coefficients, you are given the formulas and you just need to know them. So the coefficient of delivery is simply taken from the actual discharge, which is the delivery in this case. So which is the actual delivery over the theoretical delivery. So you can write as QT for theoretical. That is the idea there. So where are we going to have this? We have got the actual. This one is there. It's already there, but we do not have the theoretical. We do not have the theoretical one. So where are we going to have our QT for the theoretical? Remember that our discharge is simply equivalent to area times the velocity, area times velocity. So it means for us to have QT for the theoretical, we're going to need the area for the theoretical times the velocity under the theoretical. All these having their corresponding. Remember, I said before, if you are dealing with the theoretical values for area, you are dealing with the diameter of the orifice. The orifice is the one that gives us the theoretical values. So it means we can be able to calculate the theoretical. Our AT is going to be pi d squared, which is the orifice diameter there, over 4. So that is pi times the diameter of the orifice from our information was what? That was 0.03. So this is 0.03. So this is just a straightforward type of equation. If you know your formulas, just going to substitute your formulas, everything. You've got your AT, which was going to be 0.000707 square meters. So that is, and we also need to calculate VT, which is our theoretical velocity. So VT also is taken from our formula. Remember that theoretical velocity is the square root of 2GH. So that means our VT is going to be the square root of 2 times G, the gravitational acceleration, times the pressure head. Remember, our pressure head was given as 34,5. So this is 34,5. All right, so you're going to multiply by 34,5 here, our pressure head. So that is going to give us our theoretical velocity of 26.017 meters per second. So with these two, we can be able to calculate the theoretical discharge or delivery, which is our theoretical delivery is going to be the area of 0.00707 times the velocity, theoretical velocity of 26.017. So that's our QT in this case, which was going to give us 0.0184. Remember, like I said, discharge or the delivery, cubic meters per second. So what was the missing value? This was our missing value in this case because already our actual discharge is there. We are given before our actual discharge. We just given. All right, this is the actual discharge we have got already given from this discharge of the delivery of water. So we have got the actual there, the delivery of water. So that means we can be able to calculate the coefficient of delivery Q actual, which is 0.0125 cubic meters per second, all right, over also the theoretical delivery in cubic meters per second, all right. So that was going to give us CD, which was going to give us something like 0.679. So this is just a constant. It's a constant, guys. A coefficient. It's a constant. So there are no units. Remember, it was cubic meters per second. Cubic meters per second. So they will cancel. There's no unit there. All right. That was the idea. We're gonna need this QT. Maybe okay. If you need it, guys, we're just gonna recall. Just be able to recall. Because I'm gonna remove that. 5.12 on 5.12, they need us to calculate the coefficient of contraction in this case, the coefficient of contraction. All right, that is 3 marks. All right, the coefficient of delivery was 8 marks because you see, we calculated a lot of things, the area, and those areas, we are just gonna use them direct. The area, this, we're not gonna even calculate this again. All right, so it is said that the coefficient of what? Of contraction is equivalent to the area for the actual, that is the actual area. So we have got the actual area over the theoretical area. So the actual area, we can be able to calculate this from the actual diameter. Remember, we have got the actual diameter, like what we are given. This is the one that we are given as the diameter of what? Of the vena contractor. That's your actual diameter of 0.025. So guys, this one, I'm not going to calculate it aside. I'm just going to put it in here. Remember, our area does not change. It's pi d squared over 2. But we are using the actual diameter because we need actual area there. So it's going to be pi times. We saw that our actual diameter was what? 0.025. So this is going to be 0.025 squared over 4. So this is our actual area. We have calculated it like this over what? The theoretical area. This one, we already calculated this before. We got a 0.000707. So that was going to give us the coefficient of our contraction in this case. All right. So the coefficient of contraction was going to be 0.694. So that was going to be 0.694 like that. Okay, so that's it. That's how you play around with this type of equation. So I just hope, guys, this makes sense. I just hope this makes sense with your formulas, and this is going to actually make sense. All right, then let us check another coefficient. I just hope this board, guys, is not going to misbehave. You see how it is now doing, because we need to finish this paper. I'm not going to redo this. 5.13, the coefficient of velocity. So the moment you're talking about velocity, it means you are supposed to work with the velocities in this case. All right, so let us just write it here. I can just remove this part so that our board does not misbehave. I'm just now working with the fear of that. Am I going to be able to finish this? All right, so our coefficient is given as the actual, everything is actual on top. Actual velocity over what? Theoretical velocity. So that is the idea there. So the question is that are you having these velocities? Are we having these velocities? No, but we can find them because the velocity, once we have what the discharge or the deliver, we can calculate what the velocity. So if we divide by area, it means velocity is going to be what? The discharge over the area. All right. So that means with this formula, we can use it to calculate anything that we need because we said our velocity is going to be discharged over the area. So it means if I need the actual velocity, I'm going to talk about the actual discharge, actual area. So that is the idea there. We calculated this before. I hope we had the actual discharge. It was already there, 0.0125 over the actual area. Remember our actual area, we did not calculate. I see the problem of not calculating this, but I said you take it from what? The actual diameter. So it's going to be pi d squared, which is pi times 0.025 squared over 4. Remember your actual area formula. So that was going to give us the actual velocity in this case, which is 25,46. So it was going to be 465 meters per second. All right, remember, we calculated the theoretical velocity, this one from our VT, which is square root of 2GH. Remember here, yes, we calculated this. So we have this one. So we're going to just substitute here. So our coefficient of the velocity is going to be the actual, which is 25,465 over the theoretical, which was 26,017. So this was going to give us the coefficient of velocity, which was going to be 0.979. All right, these ones are coefficients or constants, so they do not affect anything about the units. There is no unit that you are going to consider there. All right, let us check the other part. As you can see, that was it there. All right, okay, why is it indicating this one now? The horizontal pipe, right? There we are given 5.2, a horizontal pipe with a diameter conveys water within this is calculate the coefficient using what? The Dogg formula. All right, so this one is just a direct and straightforward question. Remember our formula, our Dogg formula states that it's gonna be F, which is our coefficient of friction, times the length of the pipe, times Q, which is the discharge to the exponent of 2 over 3.026 d to the exponent of 5. So with this, do we have everything in this case? This, we have got the diameter, so we're going to have our diameter in meters. So that will be divided by 1,000, 0.09 meters. The delivery is it conveys 30 liters per second. But this is supposed to be cubic meters per second, as I talked about before. It's supposed to be cubic meters per second. So remember that a cubic meter is equivalent to 1,000 liters. So as we've got 30 liters, so we divide by 1,000. So that means our delivery, if we divide by 1,000, that will be 0.03 cubic meters per second. It's already per second. So you just work with the liters and the cubic meters. Already, the time is fine. It's already what? Per second. It's already per second. So you focus with the liters only. Then the pressure drop. What are they talking about when they're referring to the pressure drop in that case? All right, we remember HF can be calculated from the pressure drop. Remember, our HF is equivalent to the pressure drop. That is the pressure drop over rho g. That is density times what? The gravitational acceleration. So we can be able to calculate our HF, which is the head. All right. We can be able to calculate our pressure head there because we've got a pressure drop. The question was to calculate the value of the coefficient of friction. Okay, that's why they need us to calculate this one, F. Okay, so that's why they gave us this so that we can be able to calculate HF. Take note, we are given the length of the pipe. Let us just write our length so that we just finish this one. So the length of the pipe is 20 meters. So like I said, we can be able to calculate our pressure head from the pressure drop. What is our pressure drop? It is 60 kilopascal, which is 60 times 10 to the exponent of 3 over what? The density for water. For water, the density is what? 1,000 kilograms per cubic meter times our gravitational acceleration. All right, so the density for water, they can give us, but you're supposed to know it. It's 1,000 for water. It is 1,000 kilograms per cubic meter. That is the density for water. So that means we were going to obtain HF, and that HF was going to be 6.116 in meters. Remember, this is the pressure head. So with this information that we have, we can calculate F. Remember, the question there is for us to calculate F. So in order for you to calculate F, which is the coefficient of friction, we can make it the subject, or we can substitute our information there. So as for me, guys, I love to do this mathematically. Can just make this one the subject. So I'm just going to cross multiply. So it's going to be 3,026 d to the exponent of 5 times what? Times HF. So this will be 1 times this. So I'm going to have F times this. But remember, I want F. So I'm going to divide later on by what? By the length times Q squared. So this will be our F. So that's it. The coefficient of friction can be determined from this formula. So we just need to substitute our values. So that's 3.026 times the diameter in meters. That's why we have to change these units. 0.09 squared, that is to the exponent of 5, sorry, times HF, our pressure head, it was 6.116. All right, so we have used this, it's fine. So this is everything over the length of the pipe, which is 20 meters, the discharge or the delivery, which is 0.03 to the exponent of what? Of 2. This must be cubic meters per second. You were going to obtain the coefficient of friction, and that was going to give us 0.00607. No units for the coefficient of friction, as we know, guys. All right, so that is it. Just like that, we have got all the marks there. 20 marks for all this on question number 5. Question number 6, we are given the question on bearings there. 6.1, name 4 equivalent loads acting on bearings. All right, so remember that on bearings, I said there are so many loads that we're going to consider. We have got the static equivalent load. All right, so there are so many loads that we're going to consider. We've got the static equivalent. All right, the equivalent radial load. Equivalent, that's the formula, that's the, spelling there. Radial load. All right, thus we also have the dynamic equivalent. So we have got the dynamic equivalent. All right, equivalent load. We also have the basic dynamic load. Basic dynamic load ratings. These are the properties that we have. And also the dynamic equivalent axial load rating. All right, the dynamic equivalent axial load rating. So with this, they can give you 4 marks. 4 marks, you obtain 4 marks there. These are the equivalent loads that we can have on the bearings. Then a shaft is given 300 millimeters supported by 2 identical bearings. All right, so this is supported by 2 identical bearings. It is of length 600 millimeters. All right, if you check the length from this side to this side is what? 630 millimeters. All right, then the radial load carried by the shaft in the middle. There's a middle load there of what? 20 kilonewton. And all right, that's it. And there's a 5. There's also an actual load of 5 kilonewton. Okay, so you've got an actual load of 5 kilonewton on each bearing, Assume that the radial this, all right, make a neat sketch. So since there we've got a 5, going to multiply by 2 on each bearing. So that will be 10 kilonewton. So this is the diagram. Just going to make a neat sketch as for you guys, but that is what you want there. The 6.62, the dynamic equivalent load. All right, so remember I said we can calculate this dynamic equivalent load from our formula. That will be 6.3, the dynamic equivalent load. 6.2. This, okay, let's guess. This is 6.22. So this was 6.21. You're done there. The 6.22. The dynamic, you have got also this in your formula sheet. So that this is X times FR, which is our radial load, plus Y times our axial load. So you have these from what you're given, from your information, and also the coefficients that you'll be given, like these factors, they are given factors, all right? You are supposed to be given these ones. X, you're given, your X is what? 0.4 times our radial load, FR. So remember, we were given that the radial load in this case is given from, all right, there we are given a radial load carried by the middle shaft is given as what? As 20. It is taken from the middle shaft as 20. So if we have this now divided by 2, that will be a 10. So meaning to say, we're going to take this as by 10 kilonewton. All right. Plus Y being what? 1.5. That was 1.5 there. Times our axial load. Remember, our axial load is given as what? 5 kilonewton. Our axial 5. So that one for the radial divided by 2. For the axial, you take it as it is, the 5 kilonewton. So that means we're going to have our answer in what? Kilonewton. 11.5 kilonewton. All right, so as for this one, I think I'm just going to talk about this as a topic on its own, as a separate topic, so that you'll be able to understand all these formulas, where are these coming from, this and that. All right. All right, for the sake of finishing this paper, guys, we shall talk about that. All right, I think that can be able to help us. Then also I talked about this type of a question on bearings, where you are given that is the shaft load is 400 Newton, the dimensions A and B. We have got 700 millimeters here, and B 400 millimeters. These are the distances that you're given there. So the question was to calculate the bearing loads on A and BA. So the bearing load on A and B in this case, these are the ones they're talking about. All right. So this type of a question, you can use the same idea of your moments. All right. Remember your moments from your N2. So whatever that is facing down like this, it is what? It is a point load. So bearing A, it's a point load. The shaft load there, it's a point load. But bearing B is facing up, so that one is a support. So meaning to say we can just have a sketch of our diagram. In this case, we can just have it as a horizontal beam like this. Then, okay, guys, we just need a horizontal, something that is horizontal there. So we're just going to take A, because it is facing down. So we take it as a point load. Everything that is facing down, remember, it is a point load. So this is your A, but from A to B, there is a distance there, 700 millimeters. That is from A to B. But B is facing up. It's a support. Everything that is pointing up is a support. So we have got B as a support. Then from B to the end, there is the shaft load, which was also facing down. So that will be a point load again. Everything that is facing down is it is given as a point load. And we must be given this. It is given the shaft load is what? 400 Newton. So that is, we are given 400 Newton as a point load. And that is where our diagram is ending. So as we can see, we can use our moments in this case. The distance between B up to the end is 400 millimeters up to the shaft load. So considering B, we can take this about B. All right, so taking our moments about B, what is it that we have? So if we take our moments about B, we can consider, all right, so about B, you are going to see that 400 Newton is moving this way up to B, which is the clockwise direction. Remember how the clock moves. But A, as it is moving to B, it is opposing. There is this anti-clockwise. So from our laws of moments, we understand that the sum of the clockwise moment must be equal to the sum of the anti-clockwise. So the 400 is moving in the clockwise. This one is going clockwise. So that is 400. So it's going to be 400 back to B. The distance, force times distance, remember, force times distance must be equal to the anti-clockwise, that is A, back to B. So the distance there of A back to B is what? 700. So that's A times 700. So that was going to give us A. So if you simply divide by 700, because this one is a product, I can simply divide by 700 both sides. So this can cancel. So A was going to be equal to this. The product, 400 and 400 over 700. So this was going to give us 228,571 Newton. Remember, we are talking about the force, the load that we have at A and at B. So instead of us going back again using the law of moments, we can simply apply this time because we know what is at A. This is 228,571 Newton. So we can use from the forces now that the sum, we know that the sum of the upward forces must be equal to the sum of the downward forces. So what is going up? It is what? It is B. It must be equal to what is going down, the point loads. The point load at A, which is 228,571, plus the point load, which is at the end, which is 400. So this was going to give us what we have at B. So that is B was going to be 628,571 Newton. So that was the idea of the question. Just the law of moments. You apply your moments, you're done. So you study your diagram, how the presentation is given. Apply your law of moments, you're done. All right, question number 7, we are given a shaft with a diameter of 250 millimeters revolves at a bearing which is exerted this and that. We've got the coefficient of friction, the speed, calculate the power lost due to friction. All right. So the moment we talk about the force, listen, that the moment we talk about the force, guys, I mean power and force due to friction, power lost due to friction, it means we're talking about the frictional power, which can be taken from the frictional force. We can take this from the frictional force times the velocity if we have the velocity. Okay, or we can use the formula, the frictional power is equivalent to 2 pi n times the torque, that is the frictional torque over 60. This gives us the power. So we have got two formulas that we can use there. All right, let us just see. Let us just take our information down. Let us take our information down. We have the diameter. So the diameter there, that's 0.25. If we divide by 1,000 in meters, revolves at a force of the bearing. The force, which is the force of the bearing, is our normal reaction. So this is 70 kilonewton. This is your normal reaction, the force exerted on the bearing. The coefficient of friction, remember, it is the one that needs us to apply the normal reaction and the frictional force. So the coefficient of friction is 0.03, and it rotates at what? At 300 revolutions per minute. So let us just calculate necessary information. If I am using this one that involves the torque, it's a longer one. So I'm just going to start with this one because it is a longer formula. There's a lot of things to consider there. Let us start with that one. So from the formula that requires the torque, we say that the power, all right, the 7.1, the power, which is our frictional power, is 2 pi n, the frictional torque over what? Over 60. This must be in revolutions per minute. So we need the frictional torque in this case. The frictional torque, remember, torque is the product of what? Torque is the product of the force and radius. So if it is force times radius, it means I'm going to have the frictional force. Where am I going to have the frictional force? I have the normal reaction, which is the force, and the coefficient of friction. So calculate the frictional force from there. So we know that the coefficient of friction is equal to the frictional force over the normal reaction, which is the force that we are given in this case. We are given in this case the bearing, that is the force on the what? The force of 70 kilonewton, which is being exerted on the bearing. So that's your normal reaction. So you can be able to calculate the frictional force. So our frictional force was going to be the coefficient of friction times the normal reaction, which is our frictional force is going to be 0.03 times our normal reaction, the force of 70 kilonewton, which is 70,000. So you're going to obtain the frictional force from there. And that was going to give us 2,100 Newton or 2,1 kilonewton. So with this now, I can be able to calculate the frictional torque in this case, because I have the frictional force 2,100, the radius from the diameter. Remember, radius is diameter over 2. So that will be 0.25 over 2. So that's it. We're going to have the frictional torque. That is something like 262.5 Newton meter. Remember, torque is measured in Newton meters. So with this one, I will be able to calculate the frictional power, because we are saying from this formula that it states that the frictional power is going to be 2 pi times the speed in revolutions per minute, which is 300 times the frictional torque, which is 262.5, everything over 60. We are going to have the frictional power in that case. All right. So that is the idea of this question. You just need to apply exactly your information. You're done. So this was going to give us 8,246.7 in watts. So you can convert this to kilowatts if you want. It's up to you to do that. Okay. Another way that we said is that we can use the formula to find the frictional power. We must take it from the frictional force, but we must have the velocity. So we calculated the frictional force. I'm not going to talk about this the same way. If you were to use this formula, how to calculate your frictional force in this case, all right, which is this one, frictional force, you are going to do the same thing, but you need the velocity. So remember that velocity, it's pi dn over 60. So actually this is just the same. We need like same calculate, like it's just the same. Which formula you are going to choose there is the same. Like what you consider in terms of time consuming is the same. So your V is going to be pi times dn. Oh, okay, let me just calculate it. I was just thinking of just putting it on the formula. So the diameter 0.25 in meters. The speed in revolutions per minute over 60. This will give us the speed in meters per second. That's it. So that's your velocity, which is 3.927 meters per second. So with this, we can be able to calculate the frictional power. The frictional power is going to be the frictional force, 2,100 multiplied to the velocity of 3.927. This was going to give us something like 82.5 8,000, actually 246,7 in watts. So this is what you're going to have, which is exactly the same as the previous one. So it was 7 marks or 6 marks for that. Just like that. Okay. Then the other part, we are given the lathe. A lathe in this case is being driven by a motor providing a maximum input. We are given the maximum input of 3,5 kilowatt. At a speed, we are given the input speed at an input speed of 1,750 revs per minute. This is our input speed at maximum power efficiency of the machine. At maximum power, where we have the maximum input, we are going to have what? The efficiency corresponding there of what? 80%, which is 0.8. We divide by 100. Then the maximum and minimum velocities, which is the speeds in revs per minute, are given. N maximum, which is 3,500 revolutions per minute. This is on the lathe spindle, all right? Then the minimum, which is given as 25 revolutions per minute. Calculate the torque at maximum power because we are working from the maximum input. So what is going to be the maximum torque at the driving shaft of the motor? I told you guys when we did this type of a question, at the driving shaft, we are talking about input conditions there. Input conditions. Okay, what we want is to calculate the torque. So we're going to talk about this from the efficiency that we are given. Also, in the first case, there's no need for us to use the efficiency, all right? We just need the formula for this torque. But where do we take it from? Remember, power was equal to 2 pi nt over 60, where T is torque. And this is the one that we want here, the torque at this or the torque at that. Let us just make it the subject. Over 1 cross multiply 60p is equal to 2 pi nt. We want T, so we're going to divide by 2 pi n both sides. 2 pi n both sides. This cancels. So thus we are remaining with T. So T being our torque is going to be 60p, everything over 2 pi n. So that's our torque there in Newton meters. So that means if I am to calculate the torque that is at the driving shaft, from this formula, I'm just going to use this, but working at the driving shaft. And like I said, at the driving shaft, we are working with the input conditions. So it means we are going to have this as 7.21. So our torque at the driving shaft is going to be 60p. The power that we use is the input over what? 2 pi n at the input, at the driving shaft of the motor. It is at the input conditions. Input, the driving shaft of the motor. Remember, even if you want to calculate the power of the motor, P motor, it's what? That's the input, P in. You'll be given P out, and you must calculate P in. So in this case, it is the torque that we have at the driving shaft. So it is the input. So that's, let's substitute the 60 times the input power, 3,5 kilowatts. So that's 3,5 times 1,000 kilowatts. Everything over what? 2 pi times the input speed, which is 1,750. So that was going to give us the torque, which is 19,099 Newton meters. That's the idea there. So the formula for calculating the torque does not change. What changes are the conditions there. Where are you working from? The driving shaft of the motor is the input. But at the driving spindle now, we are now talking about what? The output. The spindle is now at the output. But they mentioned that the speed to be used must be at maximum speed, at maximum speed. All right, there are two things that you need there. One, it is at the driving spindle where we said we're talking about what? The output conditions. So if it is the output conditions from the formula for torque in this case, because the power is needed, so the power is going to be the output power. So you are going to need the output power. From where? From the efficiency. That is why they gave us efficiency there. That's why they gave us the efficiency, because we understand that the efficiency is equivalent to the output over the input times 100%. We understand that. The efficiency of 0.8 is equivalent to the output power, the one that we need over the input of 3.5 kilowatts. So that is going to give us the output power in kilowatt over 1. Going to cross multiply 1 times P out. Thus P out is equal to 0.8 times 3.5 in kilowatt. So you are going to obtain the output power of 2.8 kilowatts in kilowatt. That will be 2,800 watts if you want to write it as. On the formula, you're going to need to write it like that. So we have the output power, the one that we need on the formula, because I said we are going to need what? The output. It's at the output. So having this, like I said, the formula is not going to change for torque. What is the formula for torque? Our torque is given as 60 times the power, but is now at the output, over 2 pi n according to our manipulation. This is how we manipulate it. Where n is the speed that we are given, it must be at maximum speed for this one. We are given that it must be at a maximum speed. So the speed to be used must be a maximum speed. So we can have the torque there. At maximum speed. Or we can just try Tmax. So that's 60 times the output power. We calculated our output power. Remember, we got it was 2.8, right? 2.8. So the output power of 2.8 kilowatts, which is times 10 to the exponent of 3 over 2 pi times the maximum speed. They want us to use the maximum speed. Remember our N max there, the maximum speed was given as what? As 3,500 revolutions per minute. So we are going to multiply by 3,500. So that's it. We are going to have Tmax. That was going to give us 7,639 Newton meters. That's it, we're done. So it was the same approach that you're using on 7.23. They still want the same at the driving speed, but now it must be at minimum speed. So we are still going to use the same, but this time it is at minimum speed. It is at minimum speed this time. So that means 7.23, we're going to have T at minimum speed. That means we're going to have 60 times the output power over 2 pi times the minimum speed. So that's it. We are using the minimum speed there. So that's, we're going to substitute the output power. Remember, this is going to be, all right, 60 times the output power. Remember, it was 2.8 times 10 to the power of 3. Everything over 2 pi times the minimum speed. Our minimum speed is what? 25 revolutions per minute. So if we substitute this 25 revolutions per minute, we were going to have T min, which is going to give us, all right, it's actually not like the minimum, but it's at the minimum speed. When this one, the speed there, it's minimum. Not to say it's T minimum, because you think it's T maximum. The way I'm writing, guys, I'm now even confusing you. Just write the spindle there, so that like we are taking from the maximum speed. but the torque is going to be minimum. We are taking from the minimum speed, but the torque is going to be maximum. So the torque there, if you calculate properly, it was going to be 1069.521 Newton meters. So that was it. That was our paper, August 2023 exam. Let us wait. Stay tuned for the November 2023 exam on November 2023 question paper very soon at Mason African Motives. So make sure that you become part of the family by subscribing so that you won't miss that, and also to be part of the membership so that you can have access to other limited information that is limited to others. To you, it will be unlimited. So let us also consider that. From Mason African Motives, till we meet again.